Yes.
Okay. So, hi everyone. It's great to be here, and thank you for the organizers for having me. My name is Liam Schmidt. I'm a second-year PhD student from the Delta Lab at Northeastern University, and today I'll be talking about some of our results on probing magnetic anisotropy in 2D magnets using X-ray spectroscopy. So, so why are we interested in 2D magnets? Two-dimensional van der Waals magnets are have gained significant attention in recent years. They're versatile and tunable, making them ideal candidates for a wide range of devices, including spintronics uh, and multiferroics. These materials also have strongly coupled electronic and magnetic structures, leading to novel ground states. They're also highly sensitive to changes in their chemical and structural environments, which makes them unique platforms for exploring fundamental physics and technological applications. Additionally, their 2D structures allow for layer by layer construction of exotic 3D materials, providing another valuable tunable parameter for magnetic van der Waals materials. In this talk, we will focus on these 2D magnets and their many different states by changing the spin degree of freedom uh, via chemical substitution, leading to changes in the Heisenberg interactions. And we will compare and discuss the differences between two topical chromium-based van der Waals magnets using X-ray radiation to probe the spin anisotropy and characterize their electronic and magnetic states. So one of the first notable and tunable 2D magnets was this chromium triiodide, which exhibited a layer-dependent magnetic phase transition. In the single layer, it was ferromagnetic. In the tri-layer, it was ferromagnetic, but in the monolayer, it was suppressed. Following this chromium triiodide, other isostructures arose via chemical substitution, such as the CrCl3 and the CrBr3. However, despite being isostructural, these materials exhibited quite different properties, which highlights the tunability of these 2D chromium magnets via substitution and their usefulness in technological applications. Moreover, advancements in growth techniques led to new van der Waals structures, which broke both inversion and time reversal symmetry, leading to the fabrication of tunable multiferroics. And from here, by creating unique layered structures, time reversal symmetric semiconductors like CrPs4, copper chromium phosphor sulfur, and the silver chromium phosphor sulfur as well, we're investigating these. So overall, these 2D van der Waals magnets are promising for applications in spintronics, magnonics, fast switching mechanisms for neuromorphic computing, sensors, and thermoelectric devices. So shown to the right at the bottom are some of these possible 2D arrangements for magnetic ordering of these antiferromagnets, and we're going to be focusing on this Neal ordering and this zigzag ordering, which corresponds to the silver chromium phosphor sulfur and this copper chromium phosphor sulfur. It's also worth noting that recently there's been this development in altermagnets in both 2D and 3D, as well as these 1D spin chains that we'll be talking about in this silver compound, and some exotic states such as these quantum spin liquids and condo insulators. And I think it's worth noting as well that I'm currently at the European Synchrotron Radiation Facility doing an experiment on this manganese telluride, which is a thin film altermagnet. So in this talk, we're going to be focusing on this copper chromium phosphor sulfur compound and this silver chromium phosphor sulfur compound, which I'll abbreviate as CCPS and CAPS. So this copper compound has a Neal temperature of 32 Kelvin, and the silver compound has a Neal temperature of 21 Kelvin. Below this temperature, both materials are antiferromagnetic. But despite being isostructural, these materials magnetically order and behave very differently. So to the right, we show this planar overview of both materials with the chromium in blue and the copper or the silver here in yellow. So we can see in this copper-based material, we have these triangular sublattices of copper and chromium, but in the silver-based compound, we have these zigzag 1D spin chains. So despite being isostructures, we see striking differences in the magnetic susceptibility as well, which reflect this large anisotropy energy of CAPS's 1D spin chains and shows how chemical substitution can drastically change the magnetic properties of these materials. Moreover, in the monolayer limit, CCPS is multiferroic, while CAPS forms these gapless, weakly interacting spin 3/2 zigzag chains of these chromium 3+ ions. So these chains have recently been shown to be ideal platforms for spin waveguides, studying magnon diffusion, and potentially even the Ledinger liquid phase. Because they're isostructural, we know that the differences between the two materials must be due to chemical changes. Notably, the chemical substitution of copper by silver likely changes the electronic structure by introducing new chromium ligand interactions, which change the overlap or the hybridization of the chromium electrons and the ligands and introduces different crystal field splittings. And these are then reflected in the magnetic structures. So in this ongoing research, we're seeking to elucidate this mechanism which drives this magnetic order parameters dimensional transition from 2D to 1D. So one of the ways that we can measure these effects within the electronic structure is by using X-ray absorption spectroscopy, or XAS. XAS is a photon in, photon out technique, which measures how a material absorbs X-rays as a function of energy. This reveals resonances. As we can see here, we have these peaks here and a peak here corresponding to the L2 and L3 edge of the chromium ions. And these resonances reveal when the input energy is equal to the quantized gap between the electronic states. So here on the right, we show the XAS results for CCPS and CAPS using circular left and circular right polarization at the L2, L3 edge, which corresponds to exciting electrons from the 2p1/2 and 2p3/2 orbitals to the unoccupied chromium 3D shells. So this first row is the silver-based compound, and the second row is the copper-based compound. And then we then fit some Gaussians and step functions to characterize the features of the spectrum. And from these fits, we see a delocalization of the lower spin state electrons in CAPS, which then also supports existing inelastic neutron scattering results, as well as our DFT calculations. As we'll see from a simulation standpoint, this delocalization will force us to go beyond a single site model of chromium, and also highlights the role that the ligands play within the electronic and magnetic structure. As a comparison, this is some of the published data on chromium L-edge for chromium oxide and other chromium-based compounds, and we can see that the data reasonably agrees with our results. So how do you measure magnetic properties using light? Use circularly polarized light. Circularly polarized light breaks time reversal symmetry, which allows us to detect other time reversal breaking features such as spin, orbital, and magnetic moments. XMCD is another photon in, photon out based technique where you take the difference between the XAS spectra of right polarization and left polarization, and then from that you can deduce things like the number of vacancies in the d orbitals, as well as the magnetic spin moment, and the orbital moment as well. So here, the electronic density of states that's associated with the 3D orbitals may favor a specific spin direction. So when we do circular left and circular right polarization in XAS, one of the spin directions might be favored, and we might see more absorption corresponding to that polarization, which then allows us to extract the magnetic properties of a material through the spin anisotropy. So this experiment was conducted at beamline 402 of the Advanced Light Source at Berkeley. Our setup involved a 0.5 Tesla field ported along the direction of the scattered beam shown in the bottom figure here. And we report our results using total electron yield, which you measure the amount of electrons that you're ejecting from your material using a copper wire connected to a sample amount within the detector scheme. So here are some of our preliminary XMCD results taken at 15 Kelvin at normal incidence. We processed these results using an existing library, X-ray large, where we removed the background, normalized, and created fits using Gaussian peaks and step functions for each edge. Unfortunately, the data had a complicated higher order nonlinear background. The fluorescence yield was not reliable, and these shortcomings are reflected in this noisy XMCD data. An example of the quality of XMCD that we're looking for is shown here in the bottom left from our collaborators on the manganese telluride on gallium arsenide films. Taken at the Deimos beamline at synchrotron Soleil. Despite not being as comprehensive as we would like, we do observe differences in the XAS spectra, as I was saying before, which highlight the differences in the electronic structure and support existing results. So we already see that the electronic structures of CACPS and CAPS differ significantly, and we attribute these differences to distinct chromium ligand interactions and crystal field splitting effects within each of the compounds. We'll be taking follow-up measurements at ALS again within 2 weeks to get more clear XMCD data on these two compounds, and then hoping to run simulations to understand whether or not the chromium ligand interactions are driving this difference. So in comparison to our results, our collaborators' DFT results show that the substitution of copper by silver delocalizes the lower spin state electrons of the chromium atoms, which agree with inelastic neutron scattering results. So here we show the valence charge density plots, which highlight the formation of weakly interacting spin chains of chromium and of silver. And we notice that within the chromiums, there's more density, which is indicated by this darker red, which shows that the valence charge density of the chromiums is more localized. Also shown are these one-arized orbitals of the CAPS structures, which also show that the ligand interactions really drive this large hybridization between the chromium and the ligands. despite these characterizations, we still don't have a clear understanding of the relationship between ligand interactions, the electronic structure, and the magnetism for these low-dimensional chromium-based magnets. And as we can see here, these are the magnetic susceptibility for all the for 3 different isostructures: the CCPS, the CAPS, and this silver, chromium, phosphor, selenium. So we can see that the selenium-based compound with the silver looks a lot more like the CCPS compound as opposed to the CAPS, showing how we really do have this formation of 1D spin chains. So in conclusion, despite being structurally similar, CCPS and CAPS differ greatly in terms of their magnetism. Moreover, the CR ligand interactions and hybridization effects on the magnetism is not fully understood. To elucidate this, we use XMCD to quantify the magnetism and compare CCPS and CAPS through measurements of the spin anisotropy and the spin and orbital moments. And after we collect more XMCD data and have more reliable dichroism, we will compare this data to single Anderson impurity models as SAIM, and single site models, which we will numerically simulate using EDRIX, which is a Python-based package. The Hamiltonians for each of these models are shown here to the right. For example, this is the single site model. And as another example, this is the single Anderson impurity model. The difference between the 2 models is that the single Anderson impurity model accounts for this interaction between the conduction electrons of the chromiums and the ligands, and also for the hybridization or the overlap between the impurities, which are the ligands, and the conduction electrons from the chromiums. So by comparing these 2 models and comparing them to the data, we can then extract the fit parameters from the data and then be more well-equipped to understand how we can tune these magnetic states via chemical substitution. Ultimately, we hope to guide the fabrication of next-generation technologies with a focus on spintronics and magnonics. In the next few weeks, we will have collected more reliable XMC data from Beamline 402 at ALS, and from this data, we'll then compare the results to the 2 models that I discussed. In the coming months, we plan to extend our research to use X-ray spectroscopy techniques to study CR3+ moments in a wide range of chemical and crystal structures. And by doing so, we hope to provide guidance for the use of chromium-based magnets in a wide range of devices. Finally, I'd like to thank all my collaborators and thank you for your attention. And I'm now happy to take any questions.
Thank you very much for the really nice talk, Liam. The floor is now open for questions. You can either speak directly or write it on the chat.
Hi, Liam. It's a very interesting talk on these 2D materials. These are 2D materials, especially 2D ferromagnets are very interesting materials these days. I just want to know a question regarding the measurements. So as these 2D materials, they are very, I believe, surface sensitive. So, and you are measuring like, I say like light spectroscopy and these X-ray spectroscopy. So my question is, I mean, how much like these measurements affected by the surface contamination and other impurities on these 2D materials? How these measurements, I mean, affected by this?
So how are these measurements affected by
the surface contamination? Yeah, surface contamination. For example, if we want to measure, I mean like ambient atmosphere, then can we get the real measurements, or it's only the surface? I mean, atomic, some random, I mean, measurement we will get.
I see what you mean. So one of the key points about the measurements using XMCD and XIS is that we can take measurements in both electron yield and fluorescence yield. So fluorescence yield tells us about the bulk of these samples, and the electron yield tells us about the surface qualities. So ideally in the future, we want to use both to get a full characterization of the materials in both the bulk and the surface. We report these results in the electron yield because the fluorescence yield wasn't very reliable. In terms of surface contamination, these were samples grown by collaborators at Boston College, so I can't speak too much about the sample quality, but we did do previous magnetotransport characterizations and XRD to show that these really were pristine samples. I hope that answers your question.
So these are MBE grown sample or single crystal etched sample? I mean, you didn't
these were
mention
thin
about
films.
Oh, okay, thin films. Oh, nice. Thanks. Yeah, very nice talk. Thank you.
Thank you.
So I think we don't have the time for more questions. Thank you again, Liam, for the very